everybody. Welcome back from the short coffee break. My name is Moritz. I work for a company called Edgeless Systems, where we build software for the technology called confidential computing. It's the third year that I'm here, always talking about confidential computing. And since we have 2025, of course, I need to also talk about AI this year. For an introduction and a bit of a motivation behind this talk, I brought a statement from Sam Altman that sparked some discussion about a lawsuit where they are forced to store the chat data that you enter into ChatGPT, which I mean, of course, to some extent, you always have that in the back of your mind when you enter something into an AI service, that whatever that information contains might be accessible to somebody that runs the service. Some of you who are using, for example, ChatGPT might know that button where you say, hey, please don't use my data for training, and you do that by basically toggling a button. And then all you do is trust that they, in fact, not use your data for training. But for some people, that's not an option, right? Toggling a button is simply not enough for regulated industry, for companies dealing with more sensitive information, or just out of fear that your data might get lost. And hence, the, let's say, larger organizations who are providing these services, developing these models, they are thinking about how can we do that a bit more, progress this further, how can we protect the case of AI inference and protect the data that's flowing in and out of these services. And they all have different names, how they call it, private cloud, private processing, even confidential inference in the case of Anthropic. And what all of these ideas and these concepts have in common is basically the fundamental idea of isolating the service that processes your prompts and produces your responses, isolating that service with the help of confidential computing to keep the data basically protected from anybody accessing it on the back end, on the server side. We, as Edgeless Systems, we come from the area of confidential computing, and we build our own service that basically implements that concept of confidential inference, and I will use that as our running example when we dive a bit more deeper into the infrastructure. First of all, just as a short recap, or as a defining properties of what we want to achieve when we say confidential inference, is of course we're talking about an API, a large language model, or any other kind of AI model as a service. And we want to have end-to-end encryption in the sense of confidential computing. We will see in a second what that means. So end-to-end encryption, when you encrypt the stuff, client side, you send it to the service, you receive the response encrypted. Nowhere in between, basically, your data is accessible. And at the same time, we want to be able to verify this property. So we can be sure that nowhere in the backend there's something happening to my data, that the service will not just log it to some logging system or so. So some form of verification attestation. And finally, we want to achieve black box properties, meaning that the provider that's running the service, the infrastructure provider underneath, they all are excluded from our inference data. And I will just briefly introduce confidential computing for those who are not familiar with the term, what that means. I'll briefly recap my talk from last year of how we can apply confidential computing to our Kubernetes environment and protect our Kubernetes workloads. And then we'll dive a bit deeper into how we can leverage that to build a confidential inference service and look a bit more into the details. So just very briefly, confidential computing, for those who haven't heard about the term, the fundamental idea is to add to the encryption at rest and the encryption in transit, we add the feature of encryption in use. And we do that, or generally that's being done by a feature that was introduced to the hardware, more specifically to the processors, the CPUs, to keep data encrypted in main memory and isolated while it's being processed by the chip itself. And this was extended with a feature called remote attestation. So the processor has a private key to sign a report about the data that's being, the code that's being running inside this confidential computing environment, about its integrity, identity, and the confidentiality of this environment. And to this key, there's a certificate chain to the hardware vendor, so you can establish trust into some system running in a remote location based on that certificate chain and the statement from the hardware. Yeah, and that's features that have been implemented in CPUs for quite a while now and are now also available in the GPUs from NVIDIA. And that's the building block that we want to use for providing these features that I've just shown. Now, the more interesting question, how can we apply this technology to our Kubernetes workloads? Just a brief recap from my talk last year. We need one more detail about how confidential computing or this technology is being accessible to our software, and this is being done on the virtualization level. So the virtualization extension or instruction set of the CPU has been extended to allow us to create a confidential VM. Basically a VM whose memory pages are encrypted, where we can get an attestation statement for an entire VM. Yeah, that's just the way that these systems are designed, and the CPU instruction set allows us to create those spaces. And that means no other VM, not the hypervisor, no other hardware component can peek into this memory and leak any data or access this confidential VM in another way. So what we need to know is on the VM level, that's where confidential computing is applied by the latest generation of these chips. Now, when we look at our Kubernetes environment, I don't think I need to introduce that too much here. But essentially, VMs we usually find at the node level. Yeah, a node is usually either a bare metal machine or a virtual machine. But what we like to do, and especially for the case of confidential inference, is we would like to isolate just our workload, our Kubernetes pods, and the container that it entails. Hence, we need to solve the challenge of how we can apply VM-based isolation to a Kubernetes pod that's usually just isolated through container runtimes. Luckily, there exist concepts that do that already, right, for various purposes. There are, let's say, runtime classes in Kubernetes that apply VM-based isolation to pods. And one of these examples is Kata containers, a CNCF project that does exactly that. And out of the Kata containers world grew the concept of isolating those pods through confidential VMs. And this grew into its own CNCF sandbox project called Confidential Containers that basically still works partially upstream on Kata to bring that runtime class, that VM-based runtime class, and partially to develop these concept of isolating a Kubernetes pod in Kubernetes. Right? There are some more things you need to do than just the runtime class. You also need to think about attestation and how you isolate that pod, that container against the control plane and so forth. Either way, this concept is usually called confidential containers, right? Even though we speak about pods in the context of Kubernetes, it just happens to be that the term used is confidential containers. So that's why I will use that in this talk. Last year I presented Contrast, a framework we built to make your life as easy as possible when you want to use confidential containers and want to deploy an entire application into Kubernetes, generating evidence for the attestation and so forth. I'll mention that here because I will reference Contrast in the more detailed example in the end. Just that you know what I'm talking about. Okay, so what confidential containers provides us with is essentially the threat model that we can isolate one pod or one container entirely from the infrastructure. That means nothing underneath, not the hypervisor, not even someone that has full access to the Kubernetes layer can peek into your pod, into your container. And that will be our building block for building a confidential inference service. Privatemode will be the running example, the service we built based on Kubernetes. The entire architecture, or slightly simplified architecture, looks like this, and I'll just now go through how we ended up with this architecture and what all of these individual things do. So the first thing, the actual code, the actual inference. In this case, it's based on vLLM, but you can use any kind of inference engine to provide the actual inference code. A vLLM is a common, quite popular inference engine. And you can load some open source model into that, like a Llama or Gamma, or some speech-to-text model like Whisper. And from there, we can deploy that in a pod on Kubernetes, expose that through an API, and just interact with it like we would interact with a service like OpenAI. That's straightforward. So the first question now is, how do we isolate this pod? And that's coming back to confidential containers. We take this AI worker pod, and we run it in our confidential containers runtime class, meaning it's running inside a confidential VM. So it's isolated from the underlying infrastructure. Now the question is, okay, if I want to send a prompt to this now in a confidential container running service, how do I know that it's actually a confidential container that's actually isolated and it's not just some regular other container? And here, remote attestation comes into play. So we can, or the worker can obtain an attestation statement from the CPU about its integrity, about its identity, so the code that's running inside, and provide us that attestation statement. So technically, with every request, we can connect to the service, obtain an attestation statement, do some key exchange based on that attestation statement, and then establish a secure connection. One issue with that, that's quite cumbersome. So every request would need to do this attestation primitive. We, of course, can do some optimization, but then if we have multiple workers, we need to do this with every worker. So one optimization you will find in almost all scaling confidential computing-based services is some form of an attestation service. And that's also what we do with, in this case, the help of contrast, is we deploy another microservice that takes the role of an attestation service, itself runs inside a confidential container, and has the idea of transitively verifying multiple containers for us, essentially. So what we can do is we can verify this attestation service first, provide it with a configuration, and based on this configuration, this attestation service, in this case the contrast coordinator, verifies all of our other services. And first of all, that's our AI worker. So based on the configuration we provided, this coordinator verifies all of the AI workers, and then we can verify the coordinator and its configuration, and transitively we know that all containers we speak to will adhere to this configuration. How do we know that they adhere to this configuration? Because the attestation service basically implements some form of PKI, provides all of our workers with certificates, and then there's a certificate chain to the attestation service, and when we verify the attestation service, we receive the root certificate and use that root certificate to establish connections. Hence, we can do TLS connections directly to that service using that root certificate. So now transitively, we verified that the worker is running inside a confidential container. Based on that certificate, we establish secure connections. Now we know the worker that we are talking to is in fact a confidential container and has exactly the code running as it's been specified in the configuration passed to the coordinator. Now, that worker will probably leverage some form of a GPU to process your prompt. So now the question is, how do we attach the GPU to that confidential container? And right now, NVIDIA provides, let's say, a proprietary protocol to do that. And we can deploy another sidecar container that has the job of connecting to the GPU, or use the NVIDIA driver to connect to the GPU and obtain an attestation statement from the GPU and verify that this is actually an NVIDIA GPU running the right firmware and so forth, establishing or do some form of key exchange, and then we can transfer data encrypted through PCI Express to that GPU. There is an open standard that's already been established that will see life in the next generations of CPUs and GPUs called T-Device Interface Service Protocol that basically allows to attach any kind of PCI Express device that supports this protocol securely to a confidential VM, in that sense, a confidential container. But right now, it's more or less proprietary to NVIDIA. Either way, our attestation agent verifies that GPU and attaches it to our confidential VM, and then we can securely transfer data encrypted between CPU, GPU, processes on the GPU, and return the response. And then from, let's say, our client side, where we have our prompt and send it through an encrypted TLS channel into our AI worker, we have an end-to-end encryption into the GPU and back. One challenge we were facing with this kind of architecture is that when we do direct TLS between the client and our worker, something that's not showing here is that probably we have some form of API gateway that just needs to do some meta things such as routing, right? We need to know if you request the Whisper model, we need to route you to a worker that's running the Whisper model. If you select the Gamma model, we need to route you to another worker. And similarly, we want to do things such as authentication for the API. So things that not contain the sensitive prompt, but that's still necessary to provide a production-grade API. So one, let's call it optimization or a different architecture, is the idea of just encrypting the prompt or potentially any other information that's not necessary for providing the service, right? So everything that's not routing relevant. But not doing TLS between, or end-to-end TLS between the worker and the user. And therefore, we need to encrypt the prompt and establish a secret between the worker and our client that they can use for doing this prompt encryption. And therefore, we introduced a third service in this case, he called the secret service, that again runs inside a confidential container, is again verified through remote attestation by the coordinator, also, of course, then receives its certificate as part of the PKI, and we can establish a secure connection to the secret service first, set an encryption key for the prompt we would like to encrypt, and this secret service establishes a secure connection, again based on the PKI, to our worker, or vice versa, the worker will pull the secret from the secret service. And then we have we did a key exchange. Both worker and client have a symmetric key, and we can use that to encrypt our prompt, do a secure connection to our worker. It's not end-to-end. The TLS connection is then not end-to-end, but the prompt inside is end-to-end encrypted between us, the worker, and then the GPU. Yeah, so that means from this point of view, right, we have the end-to-end encryption, where we can encrypt our prompt from user to GPU and back. One detail that's missing is, I always said, right, we do the attestation on the client side. We verify the contrast coordinator on the client side, or the attestation service called contrast coordinator on the client side, and it verifies the entire deployment. And this is based on the attestation statement of the coordinator and the configuration we set there. The question is, how does the client know what it's looking for? How does the client know what should be part of this deployment? What is the identity of this worker? Meaning, what code needs to run in the worker? And when I see an attestation statement, what do I know what code this relates to? And I think that's the missing piece in the puzzle for confidential computing, is that you can, if you do it right, you can always go from source code to what's running on the actual chip. And in case of this Privatemode service, we essentially base this on reproducible builds. So you can go to GitHub, download the source code, run the build scripts, which are bit-to-bit reproducible, so you receive the exact same binaries, essentially, that will later run in this backend. From these binaries, you can reproduce the values that will be part of an attestation statement from the hardware. So you say, when I run this binary in a confidential VM, or this VM as part of a confidential VM, I will see this reference, these measurements as part of my attestation statement. And if I build this locally, I can obtain the same kind of measurements. And then I know exactly what I see as part of my attestation is what I saw from the source code. And then I can do code audits, and I can say, okay, there's actually a vLLM running in that kind of version, and there's no other code running elsewhere, or the code does precisely that in the secret service. So we can entirely reproduce the builds for this backend, and then as an end user, I can verify that what I'm interacting with on the service side corresponds to this source code, and then this is depictable to code audits. Then this completes the properties we're looking for. The end-to-end attestation, based on reproducible builds. The end-to-end encryption, so from client side to the GPU and back. And this means that not us, or potentially then if Anthropic or OpenAI would implement the same kind of system as they are outlining in these papers I've shown initially, they would exclude themselves from the prompts. So they could provide a service, or we provide a service, without us being able to access that data in the first place. And then we don't need to have this toggle, right? We can actually have a technical solution to provide this exclusion and don't even have access to the data. And of course, based on the design, right, by running this on Kubernetes, by using confidential containers, and by using some, let's say, tweaks, such as this attestation service and doing the transitive verification, you can scale this fairly easily, right? For us, it doesn't matter which worker we're interacting to, because they're all verified by the coordinator attestation service, and we just establish connections based on the certificate or on the PKI established by the attestation service. All right, so what does this give us with, right? We can, of course, run any kind of large language model, potentially, any kind of other AI model that you want to do in this kind of environment. Of course, features such as, I don't know, uploading images or audio, that's not an issue. Everything you would expect from the Inference service itself supporting, you can support through that. You can also support something like prefix caching. It requires some more attention because you don't want to share caches between different users, because then you're attackable through something like cache timing attacks or stuff like that. So you can do prefix caching, but you need to ensure, and that's something we upstreamed into vLLM, that the caches are strictly split between different users. Things that are still open to be implemented is, one thing is that with the current generation of NVIDIA GPU, this only works with a single GPU. So you cannot connect multiple GPUs, at least if you want to have the same kind of property. So you can connect multiple GPUs with Hopper, but then NVLink will not be encrypted, and communication between those GPUs will flow unencrypted through relink. This will be solved by the next generation of NVIDIA GPUs. Then you can attach multiple GPUs into a single confidential VM, potentially through the next point TDISP, right? This is the protocol I was talking about, where a CPU and any kind of PCI Express device can establish a secure channel and then do direct memory access without any performance impact. Because right now, it's a proprietary protocol. It will involve some form of bounce buffering, so encrypting the data in the CPU, stored in some unencrypted location, but in encrypted form, and then pull it from there into the GPU, decrypt it, and process it, which has some performance impact. And then some more complex things, such as, this thing is entirely stateless, right? A prompt comes in, response is returned. But if you want to do some more advanced things, such as Anthropic or OpenAI provides, such as, I don't know, RAG, you would need to have some form of statefulness and then store data encrypted inside the backend itself. And this also goes then beyond to, if you want to do something like agents, right? You could also provide, of course, a confidential agent runtime as part of the systems, but this will then involve some more complex architecture. So right now, stateless, just inference, but that's roughly what all of these papers have in common when they outline the functionality for confidential inference. That's it from me. Thank you very much. And I think we have some time left for questions.
All right, thank you. Quick question, can I create a confidential VM inside a non-confidential VM? So basically, does this only work on bare metal or also in any hyperscaler you might choose?
Good question. Depends on the hypervisor. So Microsoft has implemented this for Hyper-V. They can do nested virtualization for a confidential VM inside a VM. KVM, which I guess most other folks are running, or some form of KVM, does not have that feature yet. So you either go bare metal, or there is a workaround, depending on who you ask, of basically creating this VM outside of the host VM, and then tunneling traffic in between.
One.
Wait. Okay. Hi, thanks for the talk. I would like to know if it's probably also available on another hyperscaler, especially Google, if you can use it there, or would we also need to wait for the confidential computing between the NVIDIA device and the attestation agent?
Yeah, so confidential computing is available on all three hyperscalers and most other clouds. What we need for that precisely is confidential or a chip CPU with confidential properties and the NVIDIA GPUs, and they are available on GCP and Azure. One more thing we would like to do is use confidential containers, and this requires either going nested virtualization, right, or going bare metal. That's currently not available on any hyperscaler. So we're running that on Scaleway, which is a French cloud provider. It's available in other cloud providers, but essentially you need bare metal machines with the right amount of NVIDIA GPUs, which is currently not available on the hyperscalers.
Thanks.
No questions?
All right.
Thank you.
Thank you again.